As it is well known, for a long while in Europe there was a lingua franca for science. This lingua franca was in Latin, and this use gave the possibility to everybody in Western civilization to be part of a unique culture. For some reasons, with which we may disagree or agree, or we could be for or against, the lingua franca now for science is English. I have discovered by reading Maxwell that English can be spoken in a way which is very similar to Italian. Maxwell English is very similar to Latin, and so I don't apologize for my Neapolitan English. The aim of these lectures is to start a tradition in a PhD course to which I belong since 1997. We want to establish a tradition of classes directed to our students, which give a deep, limited in time, but deep understanding of some methods, ideas of science and technology. Okay. I already prepared such a course 3 years ago, but it was much more informal than this one. So as I will need to talk about 30 hours, I decided that what I'm not able to teach anymore in classes for standard courses in Italian universities, because of another series of reasons we don't want to talk about, I want to start from some ideas which were taught to me by my professors, I think also to the great majority of those who have my age now, which things are very, very important. I often, very often, have to repeat them to my co-workers because they are the basic ingredients for research. So these things have to be said. In my opinion, they should be said also to engineers, those who go practically in doing practical things in practical life. I don't like too much the word practice, as you understand. Okay, so I will start. Although the subject of this course is analytical continuum mechanics, I will start with some ideas which belong to more generally science, and then I will immediately particularize to something from mathematics you should know, something of mechanics you should know. Okay. You should not believe that mathematics is out of the world. Actually, we understand what is happening in the world because of mathematics. So I start with a definition which should be known by everybody using a computer. It is the basic ingredient of the architecture of everything, of every computer. So I want to talk about morphism. By the way, I studied this first year when I started my university studies. You have an operation which is defined in the Cartesian product of two sets and having its images in a third set. You have another operation which is doing the same for three other sets. Then you have suitable functions which goes from A to A bar, B to B bar, C to C bar. I say that FA, FB, and FC are constructing a morphism between this structure and this structure, if and only if the image of the composed of A and B is equal to the composed of FA and FB. This idea is under the great majority of ideas we are using in science. This idea was the idea of Neper. You should know that for a long while an engineer was characterized as the man having in his pocket a calculator with a ruler calculator. Okay? Do you know how it works, a ruler calculator? A ruler calculator is used for calculating logarithms. Why it is so important to calculate logarithms? If you want to calculate the logarithm of the product, if you want to calculate the product of two big numbers, which may be very difficult, you can think to calculate the logarithm of the product as the sum of the logarithms of the factors. When I tried to teach this several years ago, I was treated as a crazy mathematician who wanted to find a way for mistreating his students. Modern science was born when a set of monks wrote big books, the tables of logarithms. This was the first efficient computing tool based on algebra. Greek scientists were using analogic computers. But I will tell you the story in another occasion, okay? So, remark that if you consider as FA, FB, and FC logarithm, and if A, B, C are the set of real numbers and the same for the other three sets, this equation is establishing a morphism between the first and the second structure. So the concept of morphism is fundamental when we talk about mathematical structure of many, many theories. But this is a concept purely mathematical. I want now to talk about another example of morphism, which comes from a theory which in principle everybody with a degree in engineering science should know. So consider the theory of Euler beam. The displacement, the transversal displacement of an Euler beam is represented by a field U, a scalar field U, defined on an interval, and when you mathematically describe the external actions applied to this beam as a couple per unit line and as a force per unit line, which here I call mu and B, okay, then in the theory of Euler, you are required to solve this differential equation with suitable boundary conditions which are modeling the constraints applied to the beam. Okay, when you get the result, what you have got? A function, so a mathematical object. Why an engineer should know this? Because this mathematical object gives you a forecasting, a prevision of the behavior of the system you are studying. So I move a little step towards philosophy of science, but we touch it only shortly. This scheme, which describes a mathematical model, is a scheme which is due to Karl Popper. Most likely this was already known in Hellenistic times, but I will not insist in this, otherwise people will say that I'm crazy and I believe that everything was done by Greeks. I am from Naples, so I belong to Magna Graecia, and so I want to say that everything was done by my ancestors. Nevertheless, I advise you to read carefully the wonderful book by Lucio Russo, The Forgotten Revolution, which is, in my opinion, a milestone in the history of science. I will tell you that a Greek text discovered by Heiberg in 1906, translated in English, it is available in German, then in English, tells exactly what's said by Popper and describes this structure as the fundamental method for developing a mathematical model. The title of this Archimedes book is On the Method. So he was exactly talking about this. So we invent mathematical objects. If you are Platonic or Platonistic, you could say that you close your eyes, you visit the world of ideas, and you meet mathematical objects. Even if this is considered sometimes ridiculous, it has been believed by many mathematicians, including Kurt Gödel. So somebody believes that you can perceive mathematical objects exactly as you perceive physical objects. So a chair is a concept which for these people has the same reality as the concept of a function. These people are not teaching, clearly. Or if they are teaching to persons who already studied some mathematics. Because I've never seen a student closing his eyes and understanding what a function is. But they answer that there are persons with the eyes of the mind, and there are persons without the eyes of the mind. This is a dangerous subject. Okay. But, you know, just for continuing the tradition with some technological tools, this subject is very deep. You have to know about it. I simply tell you that Whitehead, the famous philosopher of science, mathematician, said, "The safest general characterization of the European philosophical tradition is that it consists of a series of footnotes to Plato." I do not mean the systematic scheme of thought which scholars have doubtfully extracted from his writings. I allude to the world of general ideas scattered through them. It happened to me in Latina that somebody started asking me questions whose answers can be read in the Republic of Plato. So there is no degeneration of genetic DNA of our students. Simply, we are not teaching what has to be taught. And we do not oblige them to learn what has to be learned. So you are PhD students, and I hope you will not organize a revolution against these concepts, as happened to me already. Okay. We are following Plato and Popper. So we accept that a mathematical model is a conjecture. We decide to build a mathematical theory. Then we ask some questions and we produce some previsions. I gave you an example for this. So Euler woke up one morning, wrote these equations, and said to everybody, this is a mathematical theory you can use. If you are able to solve this equation, you know how a beam is bent under loads. For some reasons, this is very practical and engineering, while another equation is abstract. The only difference, in my opinion, is that engineers became accustomed to this equation, while newer equations did not reach this level of saturation in the mind of engineers. Okay. Now, what about the real objects we want to consider? We imagine that for every mathematical object, we have a physical object which is corresponding to it. So, for instance, this displacement can be measured if you glue on a piece of metal we call beam. We don't call it Euler beam. Euler beam is a theory. It's something which lives here. A true beam is a piece of metal which can beat your head. Okay? Then you glue on these beams some strain gauges. You have a system of data acquisition, and you get some numbers. So you load your beam, you do some experiments on it, you get some results. Is your theory good or is your theory bad? Your theory is good if when you use this arrow coming down, so when you translate into numbers the solution of your mathematical problems and you compare it with measurements, you get coincident. Of course, there is the concept of measure error, but I mean, this also can be treated with rigorous mathematics. Okay. Why I wanted to tell you this? Because engineers are very often confusing their mathematical model with the physical object, which is very dangerous. Very dangerous. I can give you a series of examples. For instance, consider the Earth. If you want to study, the Earth is a physical object, well defined. Eratosthenes managed to measure its radius. We know it is spherical. We know many things. Earth is a physical object, okay? If you want to study the Earth in its motion around the Sun, you use the model of material particle. You write Newton equations, you write a force which is a central force between the Earth and the Sun. You painfully solve a differential equation which is not taught anymore in engineering school. Okay? You discover that trajectories of planets are ellipses. You discover the rule of the cubics of the periods of revolution compared with the principal axis of these ellipses. So you discover the time which is needed for a planet to travel around the Sun. So what you have? You have a mathematical problem. You solve it, and you use it for predicting where the planets are. Okay? Le Verrier, using this theory, pointed in a given point of the sky his optical instrument and discovered a new planet which had not been observed before. So this is a theory which is very predictive, okay? But if you want to study the seasons with the theory of a material point, you are lost. So the Earth becomes a rigid ball with a rotational. So you need the theory, the Euler theory of rigid bodies. You need to write equations which are very complicated, which were solved painfully by Arnold at the beginning of 20th century, okay? However, with this theory, you discover that when the angle of the rotational axis of the Earth is directed in a direction, in one half of the Earth you have summer, in the other half you have winter, and vice versa. So you are able to forecast what is happening in our Earth using theoretical tools. But there are earthquakes. If you model Earth as a rigid body, you will never be able to forecast earthquakes. So, when you formulate a given mathematical model, you are fixing your ideas on a given limited set of phenomena. Your theory works only for that class of phenomena, and it doesn't work for others. Okay, the theory of everything is not possible. It is not existing. Okay, I want to tell you that this is very dangerous. I mean, not to ignore this point is very dangerous. Did you know that Navier tried to study the beams using the theory of atoms? If you are an extremist, you can say, matter is made of atoms. Everything is described by the theory of atoms. A beam is made of atoms. I write the equation of the beam starting from the theory of atoms. Of course, you get some interesting results with statistical mechanics. I don't deny this. This is very important. But it is not very wise to study a beam considering what is doing every atom constituting it. So, in general, it is very wise to distinguish the model and the physical object which is described by that model. Different phenomena occurring to the same physical object may need, for their description, different theories. I simply tell you something. This scheme is due to Popper. However, there was another group of philosophers of science which we may call Inductionists. Okay. They believe that this scheme must be reversed. They say that everything starts from observation, and then the arrows are pointing towards the mathematical objects. Okay, this is a point of view which is very dangerous also, because unfortunately there is no model describing everything. When you believe to have reached the total description of a class of phenomena, then you are in troubles. Citing Popper, whenever a theory seems to be to you the only one possible, then you have a sure sign that you have not understood both the theory and the problem you wanted to solve. By the way, this is written also in Archimedes' method. Okay, so why this at the beginning of a course in analytical continuum mechanics? Because we will talk about different models for the same physical object. And we will need to distinguish between the concept of state and the concept of configuration. A state is related to a physical object. A configuration is the mathematical model used in a given theory to describe the state of that point. So, for instance, if you are studying the Earth in the motion around the Sun, the state of the Earth is modeled with 3 coordinates, x, y, zeta, for instance. So 3 real variables which describe the configuration of your system. If you are studying the motion of the Earth around the Sun, if you have the motion of Earth and you model it as a material point, then the configuration is given by 3 real numbers. The motion is given by a function mapping time into a triple of real numbers. Okay? When the state is evolving in time, if your model is predictive, then you know in every instant where the Earth is. Of course, here the analysis can become more delicate. The Earth has a radius of 6,000 kilometers. The motion around the Sun involves hundreds of millions of kilometers. So, in the motion of the Earth around the Sun, 6,000 kilometers is a very small number. So you can neglect the dimension of Earth in this model. Okay. If the Earth needs to be described as a rigid body, to the coordinates x, y, zeta, you need to add the 3 Euler angles. So the system becomes a system with 6 parameters characterizing the configuration. The state is always the same. Okay? It's an object in the real world of facts, phenomena. When you want to study earthquakes, then you are obliged to model Earth as a deformable body in which a function mapping 3 numbers into other 3 numbers, we will go in deep details to talk about this model, okay? So the state of the system is modeled with a function, okay? This happens also in the theory of the beam. When you describe the shape of a beam, you need a function which is defined in an interval, and this function is telling you the displacement of the center of mass of every section in this deformation. So the shape of the beam is actually the graph of this function. Okay? So I want to shock you because I want to talk about a subject which is considered too mathematical by many. If you consider, for instance, the set of continuous functions defined in the interval AB, you easily discover that it has a structure of vector space. If you sum 2 continuous functions, you get a continuous function. If you multiply a continuous function times a scalar, you get another continuous function. okay? You have the opposite of a continuum function. You have the zero function, which is the null element of the vector space. So this animal has a similar structure as R3. So vector spaces are often used for building configuration spaces, okay? But there is an enormous difference between C0 and R3, and everybody who is handling a computer should know it. How many numbers do you need for characterizing a continuous function? Infinite numbers. So, a mathematical model can be called finite dimensional if a set of finite real parameters characterize its configuration. While a mathematical model is infinite dimensional if you need infinite parameters. Then, you know, Weierstrass was not a crazy mathematician. When he met C0, before the invention of computers, he asked himself, can I approximate every continuous function with a polynomial? Polynomials are a particular class of continuous functions which have a very peculiar behavior. If you know the coefficients, which in general are finite in number, you know the polynomial. So you can try to describe any continuous function with a suitably chosen polynomial which belongs to a finite dimensional vector space. If you talk about Pn, the set of polynomials defined in the interval AB, everybody who is fighting with computers, maybe without knowing, is doing something like that. Consider the polynomials of order n in the interval AB. Then you have A0 plus A1x plus ANx to the power n. This is the generic polynomial. The function has to be estimated replacing to x the suitable value in the interval AB. But this polynomial is uniquely characterized by A0, A1, AN. So it is isomorph to Rn. So it became finite dimensional. Now, when you are using a computer for solving an equation whatsoever, you need to find the right approximating finite dimensional space for trying to find, for having a hope to find your solution. So, the distinction between infinite dimensional configuration space and finite dimension configuration space is very important, but we have to know that computing implies reducing an infinite dimensional model to a finite dimensional one, and this is very difficult. For doing this, you need to develop numerical methods. Numerical methods are not practical. There is a theory behind them. You are not turning, you're not screwing things for getting it work. You have to understand what it is doing. Otherwise you get pictures without knowing what you are doing. So Weierstrass invented the fundamental theorem for approximating any field with a class of field which belong to a finite dimensional vector space. Okay, so in both finite dimensional and infinite dimensional models, the big problem is to find the equations which allow you to give predictions. Okay? You need to be able to predict what is happening. It is not clear what Greeks invented, because partial differential equations are surely born after Neper. The way which we are using for predicting the evolution of systems is to formulate suitable differential equations which govern the evolution of the system. So the idea which we have in mind is the following. And this you can read. I could not find the citation, but I will let you have. This you can find in D'Alembert article of the Encyclopédie. La cinématique d'abord. You have to start with cinematics. So you need to decide which kind of motions you want to introduce in your model. Once you have characterized the set of motions, so you have your space of configurations and then your set of motions, then your problem is, where are the equations which I have to solve for forecasting the behavior of my system? Now, the art of scientists is to find these equations. So we have to talk how all our predecessors invented the equations which govern the evolution of systems. They are not coming out of the blue. Somebody believes that God, together with the 12 tables, wrote also Schrödinger equations, Lagrange equation, the equation of beam. I mean, one should, if you ask to somebody from where heat equations are coming in this faculty, he will answer you, we already knew them. Okay. Or I've seen some classes in which the professor enters the room and writes Maxwell equations, and then he starts deducing from them results. Okay. The question is, from where they got these equations? Why they got these equations? Okay, now, if you are an engineer, you can live with the general information. These are the equations for you. For instance, you are a structural engineer. You know the set of equations. They can give you a program, a software. You use it, you are happy. You should know more or less what you can do with this software. But if you want to get a PhD in theoretical and applied mechanics, you are assumed to invent new equations or to find new solutions of already known equations, or to describe a weak point of an equation in describing some phenomena. So in a sense, you are obliged to spend some time in what we could call meta-theory. So the theory describing how to construct theories, which was not invented by me, unfortunately. The first version of this, but this is my fixation, maybe you find it in Archimedes, but D'Alembert, Jean Leron D'Alembert, formulated this theory. Then Lagrange developed it. Okay, so the aim of this course is to teach you how mechanics can be invented following a recipe, a strategy. You have to learn the meta theory by D'Alembert, Lagrange, Piola. This is my last fixation. Okay, you know, at least I'm changing fixations. This is a recent one. I'm translating it in English, so you will soon be able to read everything in English, because Italian is difficult. Okay. Now, in general, you consider the set of motions. So let us call M the set of motions. Don't believe I want to show you that I'm a good mathematician, or I want to force you to learn some mathematics. I don't want to tell you how this set is constructed, because there are many examples. If I give you now an example, I limit yourself. So you have to introduce a space of configurations. Then you have to introduce a set of motions, which are mappings defined in a time interval whose values are in the set of configurations. Remark that I'm not telling you that this function is continuous. I'm not telling that you can derive it. Actually, did I tell you that the space of configuration has a topology, a matrix, something? I want to be general. Then, in every case which we will study, we will learn how we are constructing the structure of this space. So consider the space of motions. Not Lucio Russo, not me, I forgot, I will let you know. A philosopher of science and expert of Greek science claims that the first formulation of the least action principle is due to Archimedes of Tarentum, again South Italy, more or less 3rd century before Christ. So the idea is the following. Natura, the nature, is choosing the shortest way. So you have to define in the set of motions, so given a motion, M, which belongs to the set of admissible motions, you need to tell how much a real quantity, which we call action, amounts, which is the value of this real quantity when the motion is the given one. The idea of D'Alembert, as explicitly written in his books, is the following. Nature will choose the motion which minimizes action. Of course, this is still a rather abstract theory, because we have to tell you how much is the action in some examples. Hamilton after long investigations decided to introduce kinetic energy and potential energy for a given mechanical system, and to say that the difference between kinetic energy and potential energy manipulated in a certain way gives you the action which nature wants to minimize. Okay. Recently, it is very often studied a problem which is causing a lot of troubles to scientists. a bone, when loaded, not only deforms, it reacts. And some cells start building somewhere matter and absorb somewhere else matter to construct a tissue which is more efficiently responding to loads. Okay? Nobody knows which is the action which has to be postulated for describing these evolutionary problems. For this reason, we do not know very much about this phenomena. Until we will not understand how to construct an action for this kind of phenomena, you write equations without knowing if they are well posed, if they can be solved, if they have a physical meaning, if you have conserved quantities which you can follow during the evolution of the system. So the meta-theory which I'm talking about is a meta-theory which tells you the general structure of a theory and gives you some directions when building a theory. Of course, there is not yet a meta-theory which, given a phenomenon, is writing for you the equations. So this is left for us, but could even not last forever. I mean, if you have read Asimov, you will know that already many people imagined a world in which robots are inventing equations. Okay? So, I could go in more details. For instance, everybody knows that for finding minimum of a real valued function, so a function defined in the set of real numbers whose values are in the set of real numbers, or if you have a function f defined in Rn whose values are in R, I hope that everybody here knows that if the function f can be differentiated, so if you have all partial derivatives of f and these partial derivatives are continuous, then maxima and minima of f can be found solving the equation grad f equals 0. This is the Euler-Lagrange equation for an action defined in a finite dimensional vector space Rn. So the positions which, in this case, we are talking about equilibrium, of course. The stationary motions for your system are such that the gradient of f is vanishing. So now, but I will refrain from doing this, now I could start building a mathematical structure on M in order to be able to calculate the differential of A. This theory was developed in a draft form by Lagrange when he was 17 years old, and has been formalized in rigorous mathematical terms by Fréchet much later, at the beginning of 20th century. So there is a way for introducing in M a mathematical structure which allows you to calculate the derivative of an action, and therefore to construct the equivalent condition grad f equals 0 in the most general setting. Okay? Now, this in a dream, in a Platonic world, should be the method. À l'école polytechnique, they are doing in this way. À la grande école de Ulm, they are doing in this way. Okay, but I decided to be realistic. I will show you how to do in several cases, and I hope that you will find it so powerful that you will be willing to learn how to construct in general theory when M is more general than the cases we have decided to study. Okay? So the meta theory, we end here, has a weaker version. This you will understand better later, but I want to tell it now. If you imagine to be able to write A of M plus delta M minus A of M, I tell that Lagrange did it when he was 17 years old in order to make you feel guilty if you don't want to learn it. Okay? So you have something which is nearly equal because you are linearizing this variation, and you say that there is a linear operator which applies to delta M, which is approximating this finite increment. Okay? Okay. When you write this equal to 0, you have exactly the same thing as saying that grad f scalar dx equals 0, which is the condition of first variation vanishing. This was for every dx. Okay? An Italian scientist, mechanician, not an historian, whose name was Vailati, 1890 something, discovered this formulation for a physical law for equilibrium and motion of body in some Heron books. This is what we can call the principle of virtual works, or the principle of virtual powers, or the principle of virtual velocities, depending on the age. Now it is very trendy to call it the principle of virtual powers. Okay, because dm is infinitesimal, we are rigorous, so we use velocities. Okay, but I believe that the most clever way to call it is the original one by Lagrange, principle of virtual velocities. We can formulate it in this way. Take your motion, add a small virtual velocity to this motion, linearize the action increment, then calculate this first order increment. It has to be 0. For some historical reasons, dissipative systems cannot be easily studied by introducing an action. Lagrange, who was a student of Jesuits, so he was very able to adapt to circumstances. You know what he said? No problem. I introduce work. So when I formulate my model, I have a motion, a set of motions. Instead of introducing an action, I consider for every motion and for every variation of this motion a quantity which I call the work done by all interactions involved in our phenomenon, starting from m when you vary m of delta m. So in a sense, but this is not a first variation of something. This is the first order approximation of something, but it is not the exact differential of something else. If you have studied something in thermodynamics, this concept is taught in physics, first classes of physics. Okay? So the idea is that you have a variation of work done on a variation of motions. So the meta theory of Lagrange, second version, that one which resisted up to now, is the following one. Do you want to describe the evolution of a system? You must find the work done by all interaction which take place in the motion of your system. So you will have external actions, internal action, inertial actions. We will learn how to distinguish these different actions in some particular cases. Your prevision about the motion of your system is the solution of this equation. A motion which is really showed by your system is such that the sum of all works for every variation of motion are equal to 0. We will see that all equations written in every book can be obtained in this way. I strongly suspect, but I'm not sure, that every equation written in every book can be obtained by the minimization of an action. But this is controversial. This is accepted by everybody. So we will talk about this mainly, but I will try to persuade you that I'm right about action. Now, before ending, of course, this is a preliminary, so this is the first, then we will go much more technical. Don't behave as your younger colleagues who are shocked by the second lecture. In my opinion, nearly always the equations for a given phenomenon in a given model were formulated using this strategy. I tell you an example, which is my last fixation, which is, in my opinion, very meaningful. Piola was a young mathematician who studied in Pavia. He was pupil of a famous mathematician, Vincenzo Brunacci, who started a terrible fight against French mathematicians, claiming that he was finding Laplace equations for capillarity before Laplace. So there was a violent discussion about this. Piola was a very rich nobleman, so he never needed to accept a chair. He was offered a chair also in Rome. He never wanted to become professor. He spent all his time doing research home. He could do it. Okay, but all his pupils became professors. In particular, Francesco Brioschi became the founder of Politecnico di Milano. So it can be considered a caposcuola. There is a metro station, a place and a statue for Gabriele Piola in Milan. So in Milan, they, in my opinion, correctly consider him a great personality in science. So he woke up one morning and he decided, I will generalize fluid mechanics by Lagrange in order to extend it to solids. He found an action. He knew it is dangerous to deal with actions, so he formulated immediately a principle of virtual works. He did many calculations without vectors, so without vector calculus. So it was a nightmare. He wrote something like 500 pages, and he found Piola stress. And he found, with Piola transformation in the Eulerian configuration, Cauchy stress. But he was not member of the French Academy of Science. So he needed 3 years for having his paper published. In the meanwhile, Cauchy wrote his famous paper about stress, Cauchy stress. Poisson attacked Piola papers, telling that all this is garbage to mathematics. So the Piola books remained there, written in Italian, so nobody could read them easily, and here and there his ideas are coming out. In particular, I do not know why, but in Berkeley they call a given transformation Piola transformation. When I asked my friend David, who is teaching this in Berkeley, where you read it, he told me, I do not know. I heard, I repeat it. So there is a tradition from Milan to Berkeley, a variational tradition, teaching continuum mechanics based on the principle of virtual works. So I want to fight this battle, but this is not a battle for meaning that we are better and the others are worse. In my opinion, there is no other way. When you have the equations, you find always a way for justifying them. The big problem is finding the equations. The true big problem is to find the right equations. And in my opinion, this is the only way. Okay? I will try, so all the other lectures will be an effort of proving